Quantum mechanics. Bohr's model does not explain the emission spectrum for atoms containing more than one electron. It also does not explain why extra lines appear in hydrogen emission spectrum when a magnetic field is applied. So Heisenberg came up with his Heisenberg uncertainty principle. And all that says is that it's impossible to know simultaneously both the momentum, which is symbolized by P, and the position, which is symbolized by X, of the particle with certainty. So he used this formula, delta X times delta P is greater than or equal to Planck's constant divided by 4 pi. So applying Heisenberg's uncertainty principle to the hydrogen atom, it tells us that in reality the electron does not actually orbit or circle the nucleus in a well-defined path. So Heisenberg's uncertainty principle helped us fix the issues that Bohr's model had with explaining spectrums for more than one, or for atoms that have more than one electron, which then also led us to the different properties for those elements. So why do we study Bohr then? Bohr did make a significant contribution to our understanding of atoms, and his suggestion that the energy of an electron is in an atom is quantized remains unchallenged. But his theory did not provide a complete description for electronic behavior in atoms. Erwin Schrödinger formulated an equation that describes the behavior of and energies of particles. So Schrödinger's equation incorporates both the particle behavior, the mass, and wave behavior, which is the wave function, which depends on the location in space, or the location of the electron in the atom. So Schrödinger's equation began a new era in physics and chemistry called quantum mechanics, or wave mechanics. Now his equation is high calculus, which is beyond the scope of this class. But if we calculated where the electron most probably is located, then we get these pictures called electron densities. So if we plot where the electron should probably be located, we actually start seeing a shape of these electron clouds. So the quantum mechanical description of the hydrogen atom tells us we cannot pinpoint an electron in an atom, but it does define the region, or these 3D areas, this electron density picture, where the electron might be. So electron density gives us the probability of the electron, where it should be found. The atomic orbital is the wave function of the electron in the atom. So when we say orbital, we're really meaning the probable location of the electron in space, described by the wave function squared. And that wave function, remember, is coming from Schrödinger's wave equation. Quantum numbers are used to describe the distribution of electrons in the hydrogen atom and others. These are derived mathematically from the Schrödinger's equation for the hydrogen atom. Now, the fourth quantum number describes the behavior of this specific electron and completes the description of the electrons in the atoms. So the first three numbers all come from Schrödinger's wave equation, and the fourth one describes that specific electron. So the first quantum number is the principal quantum number, or n. N can equal an integer, so it has to be 1, 2, 3, 4, 5, 6, so on and so forth. It determines the energy of the orbital, although not the case for many electron atoms, and we'll get to that later. It relates the average distance of the electron from the nucleus in a particular orbital. The larger the n value is, the greater the average distance from the electron is from the nucleus, and therefore the larger the orbital. So when we're on the first energy level, n is equal to 1, and we're close to the nucleus. N is equal to 2 is a little bit farther out, and so the orbital gets larger. N is equal to 3, we're on the third energy level, the third principal quantum number, and it's an even larger orbital. The angular momentum quantum number, or L, tells us the shape of the orbital, and its values depend on n. So for a given n, let's say n is equal to 1, then L has to be equal to 0 all the way up to n is equal to 1. So if n is equal to 1, L has to equal 0. If n is equal to 2, L has to equal 0 or 1. If n is equal to 3, then L has to equal 0, 1, or 2. If n is equal to 4, you have 0, 1, 2, or 3, and so on and so forth. So what those L values are telling us are our sublevels. So the 0 represents our S. So if we look at n is equal to 2, then we can have a 2S, or 1 is P, so we could have a 2P. 3, we have a 3S, or a 3P, or a 3D. So the angular momentum quantum number is telling us the sublevel, which we label S, P, D, or F, and you can theoretically keep going. So after you get to F, you just start going based on the alphabet, F, G, H, I, and you would skip over S and P. The third quantum number is the magnetic quantum number, m sub L. It describes the orientation of the orbitals in space. M sub L depends on the value of L. So the m sub L value would go from a negative L through 0 up to the positive L. So if L is equal to 0, m sub L has to equal 0. If L equals 1, m sub L has to equal negative 1, or 0, or plus 1. If L is equal to 2, then m sub L has to equal negative 2, negative 1, or 0, or plus 1, or plus 2, so on and so forth. So remember, these are my sublevels, S, P, D, and F. So what the m sub L is describing is the orientation of the orbital in space. So this is my sublevel, this would be my orbital. So the S sublevel has 1 orbital. The P sublevel has 3 possible orbitals. The D has 5 possible sublevels, and the F has 7 possible sublevels. Now the fourth quantum number that's not related to Schrödinger's wave equation is the electron spin. The emission spectrum could be split by the application of the magnetic field. So when we looked at hydrogen's emission spectrum and we apply a magnetic field, we actually see divisions in the lines, or it's split in half. And that's because the electron is spinning. So assume electrons are like tiny magnets. The electrons spin on an axis and can spin clockwise or counterclockwise. So m sub s either is a plus 1/2 or a minus 1/2. And it doesn't matter which value we apply, but it has to be plus 1/2 or minus 1/2. When we draw our orbital notations, we show that using the up and down arrow. Alright, so this is just a table of our quantum numbers that are based on Schrödinger, so just the first 3. So looking at the first 3 quantum numbers, we can see that the S sublevel has 1 orbital, 1s. The P sublevel has 3 orbitals, and the first time it shows up is in our second energy level. The D sublevel has 5 orbitals, and it first shows up in our 3D, or in our third energy level. So atomic orbitals. What are the shapes of these orbitals? They really don't have a well-defined shape, but it's convenient to think about the orbitals having specific shapes, particularly when we start discussing information of chemical bonds in chapters 9 and 10. So the s orbital, there is about a 90% probability of finding the electron within a sphere surrounding the nucleus. So if you look at your electron densities, you can see that when we plot those diagrams, they tend to look like a sphere. If we keep coming out from the nucleus, if we start to calculate those values of the different energy levels, they still look like a sphere, but the sphere is getting larger and larger. So the boundary surface diagram encloses about 90% of the total electron density in an orbital. Each s orbital is spherical in shape and increases in size as we move outward. As we increase the size as we move outward, we're also increasing the amount of energy. Now the p orbital, these start again in the second energy level, and m sub L tells us that if n is equal to 2 and L is equal to 1, then m sub L has to be negative 1, 0, or plus 1. So we get 3 different views of the p sublevel. So if we look at the diagram, this subscript here, x, y, and z, describes the axis that the orbital is found on. All three orientations have the equal amount of energy, so there's really no difference between 2px, 2py, and 2pz. So they're degenerate. There's also no relation to the m sub L values -1, 0, or +1. All the m sub L is telling us is that there are three possible orientations. And when we graph those orientations, that's where we get the subscript from. Like the s orbital, as we go into higher energy levels, the p orbitals become larger. So you have your 2p, your 3p would be larger than your 2p, and the 3p would have more energy than your 2p. Now d orbitals and other higher energy orbitals. The d sublevel starts when n is equal to 3. And so your m sub L value, your L value would have to be 2. So your m sub L value would either have to be -2, -1, 0, +1, or +2. If we were to graph those different areas using the electron densities and Schrödinger's wave equation, these would be what our orbitals would look like. So again, look at your subscripts. They're telling you how the orbitals are in line with the axis. They don't match up to a -2, -1, 0, +1, or +2. It just describes it how it looks on the axis. Remember, your m sub L value is just telling you how many different versions you have. Now, all the d orbitals are equal in energy, so they're all degenerate, and become larger as you go to higher energy. So your 4d is larger than your 3d, and your 4d has more energy than your 3d. Any orbitals that are higher than d, like your f, are specifically your f, is important to atomic numbers greater than 57, but their shapes are more difficult to represent. So we're not going to really go past the f orbitals in this level course. Alright, so let's start putting these quantum numbers together. So given the values of the quantum numbers associated with the orbitals in the 3p sublevel, so the big number there would be our principal energy level, n, so n would have to equal 3. Well, if n is equal to 3, then L can be 0, 1, or 2. Now the p tells me I'm talking about L is equal to 1. So if n is equal to 3 and L is equal to 1, then my m sub L is going to be -1 or 0 or +1. Now we don't usually write it out like that. We usually just write 3, 1, -1. Or it could be 3, 1, 0. Or it could be 3, 1, +1. So that would be the answer to that question. What is the total number of orbitals associated with the principal quantum number n is equal to 4? Well, if n is equal to 4, then L is going to be 0, 1, 2, or 3. It goes from 0 up to n-1. Well, if L is equal to 0, then m sub L has to equal 0. If L is equal to 1, then m sub L equals -1, 0, or +1. If L is equal to 2, m sub L equals -2, -1, 0, +1, or +2. If L is equal to 3, m sub L equals -3, -1, -2, -1, 0, +1, +2, or +3. So, how many orbitals do I have total? 1 plus 3 plus 5 plus 7. So that would give me 16 orbitals. Well, if you look at your n is equal to 4 and we have 16 orbitals, to figure out your number of orbitals then, you can simply do n squared. Give the 4 quantum numbers for each of the 2 electrons found in the 5s orbital. 5s. So n has to equal 5. Because I'm in the s sublevel, L has to equal 0. Because L equals 0, m sub L also has to equal 0. Now I want to give it for each of the 2 electrons. So my spin is going to be plus 1/2 for one of my electrons. For my other electron, it's going to have the same first three quantum numbers because it's in the 5s. So the only difference then is going to be that fourth quantum number, and it's going to spin the opposite direction, so negative 1/2. Why is it not possible to have a 3f, but 4f is allowed? Again, our quantum numbers tell us this. So if n is equal to 3, then L has to be 0, 1, or 2. So F is not a possibility because F would mean L is equal to 3. Now if n is equal to 4, our L value can be 0, 1, 2, or 3. So the 4F is allowed because we have L is equal to 3. So the energy of the orbitals. Hydrogen's electron has energy related only to its energy levels. But for the many electron atoms, it depends also on the angular momentum quantum number as well as the principal quantum number. So we actually get Aufbau's principle. And so we fill on the diagonals, and there's a blip when it comes to the P and the D. So after you fill the 3p, you fill the 4s, then go back and fill the 3d.